Welcome to part 2.1.4 Browsers of the DeepCode SummerAcademy on debugging. By the way, if you like what you see, make sure to subscribe. First, we need to have a basic understanding of the architecture of a browser, and I picked Chrome here as our example. Because we will use these terms quite often, let us define a few terms. So GPU, or graphical processing unit, is actually the graphics card within your machine. And in most modern computers, it actually has more transistors, it's more complex than the CPU, which is the central processing unit, or what everybody calls the processor, which is necessary for mathematical calculations and stuff like this. Another term that we will use now is process versus thread. So in an operating system, you have processes. Multiprocessing means several processes can run next to each other. Each process has its own memory and has its own time slice of calculation for it. And the operating system now makes sure that these processes can work next to each other and do not interfere with each other. Within the process, we have what is called a thread. So these are like individual worker pieces of code that are running in parallel within the process. They share the same memory and they share the same process. So why having threads? They share the same resources of the process. And so they can easily cooperate and work on the same, for example, memory that is shared by the process with them. They are faster to establish. You can very fast spawn up a new thread within a process. But the downside is that if one of the threads within a process crashes, normally the whole process crashes. Now, in between processes, the interesting part is that they don't share the same memory, for example. So the operating system can normally recover if one of the processes crashes. It simply deletes that process and continues with all others. A downside on this is that the processes are a bit more expensive to generate. It takes a bit longer to generate a new process. The upside is, in between processes, we are much more safe, we are much more secure than if we would only have threads. Chrome makes heavy use of processes. So for example, there's the browser process with a utility process that have individual threads inside them that are then taking care of storage, of networking, and also on displaying the Chrome, like the menu parts and the tabs and these things. Then there's a GPU process that manages one of the most important resources, the GPU. Next, we have renderer processes and plugin processes, and these are actually the ones we will look deeper now. So if you ever ask yourself why Chrome has so many processes, now you know. In Chrome, the browser process is responsible for everything that is around your website. So the open-close buttons, menus, navigation bars, stuff like this. The renderer process is responsible for everything that is on the website, and it makes also use of plugin processes that might help to render the elements. And all of them are actually using the GPU process to really print something on the screen. Having these vast amounts of processes actually help Chrome to secure the communication in between the elements. So no plugin can take over the website or something like this. It's separated by using different processes. Also, if one of the rendering processes crashes, you will see this in the Chrome tab, but Chrome won't crash and not crash all of the websites with it. Now let us dive a bit deeper on what happens actually when we are loading a website and how performance is literally depending on us to be nice as developers. Or in short, I want to help you make sense out of the performance tab of the developer tools of Chrome. You can imagine how browser and renderer process talk to each other when starting to load a new website. In the process, the renderer process will actually start several threads to help to build up the website and display it. By the way, the browser tries to optimize every step on the journey by speculating, looking ahead, parallelizing tasks. And as a developer, you can bust this process if your application does not behave correctly. That will lead to a performance penalty. Another quite interesting aspect is that when you are navigating to a new page, Chrome actually starts a new process, uses the old process to calculate the unloading part while already loading the new website in the new process. So let us follow how a website is actually loaded and rendered in the browser. And it all starts with the browser process feeding the rendering process the HTML that comes in as a string. So the renderer process, as we see it here, uses the main thread to parse the incoming string into what is called a document object model, or DOM, which is a tree-like representation of the HTML in memory. There are two interesting types of tags that we need to know about. The first type is actually a tag that refers to an outside resource, so something that has to be reloaded by using the network. And as you can see, I'm using link or image as an example here. So in this moment, the renderer process, the main thread, is actually asking the browser process to use the networking elements to load these resources and make them available to our main thread here. Another interesting tag that might happen is the script tag. And whenever the main thread, by parsing the HTML, hits a script tag, it actually stops building up the DOM and starts to execute the script. This is something that HTML is actually asking for. And the reason for that is that the script could actually change the document object model. It could add new elements to the DOM. It could delete elements. And this is something that the browser wants to make sure is captured before it continues in the process that we will see how this all is rendered here. So there are some ways that you as a developer can actually help the browser to be very fast, or as fast as possible, in this aspect of the rendering of the website. You can actually give hints. So there's the hint of async or defer that you can use with JavaScript to make sure the browser understands this will not interact with the DOM in the loading phase. So I can actually, so to say, asynchronously execute the JavaScript in the background while I continue in the rendering process, as we will see it. Another thing is that you can assign a forced preload to the JavaScript, which means this JavaScript needs to be executed right before anything else is done, and it will actually force the browser to stop anything and work on the JavaScript. For sure, you noticed HTML is a very forgiving standard. So even if you forget closing tags or so, HTML just continues to render and does the best with it. Next step on our journey is to generate the styles. So the main thread here is collecting all the style information. If you do not provide style information, you end up only using the styles that are part of the default deployment of Google Chrome. So there's a default style sheet. If you provide styles, your styles will overlay the default style sheets that are actually deployed with Google Chrome. Out of this, the renderer process generates the computed styles. And if you go into Google Chrome Developer Tools, in the styles you will find a tab with computed styles, and this is actually the results of this process. Now that we have document object model and computed styles together, the main thread can start to layout. And what it does is it generates what is called a layout tree in memory. This is actually a quite challenging task. Even the simplest page layout, like a block flow from top to bottom, has to consider how big the font is and where the line breaks need to be, because those affect the size and the shape of the paragraph, which then affects where the following paragraph needs to be. In the next step of the journey, modern browsers use an optimization technique, which is called compositing. And compositing is a technique to separate parts of a page into layers, rasterize them separately, and composite as a page in a separate thread called compositor thread. If scroll happens, since layers are already rasterized, all it has to do is composite a new frame. Animations can be achieved in the way by moving layers and composite new frames. In the past step, the main thread generated the layer tree. Now, using this layer tree, the compositor thread can start to build a paint record, so literally building a little script, so to say, where to draw what and where to draw text and stuff like this, and feed this into these raster threads that are then actually responsible for painting pixels. They are communicating to the GPU process to paint the pixels on the monitor. So what I showed you was even a simplified journey from incoming HTML to really seeing something on the screen. And you can imagine this will run all of the time, maybe 60 frames per second, because you want to see animations and video being played on your website. The point that you should get out of this is it's actually a quite complicated process, and it needs every help we can give it as a developer to make it as performant as possible. The good news is Chrome tries to optimize every step in this journey. We can help it doing so by, for example, annotating the JavaScript as I mentioned before, or by sticking to the best practices of the JavaScript framework that we're using. So might it be React, might it be Vue, or whatever you're using, stick to the best practices. Because these are designed to reduce the number of re-renderings as much as possible, and therefore optimize the page load times accordingly. So this was our short video on browser rendering pipelines. Tomorrow we will dive deeper into linters with our SummerAcademy and the part 2.1.5. See you then!